Hello, good people. Good morning, good evening, good afternoon, whatsoever, everyone, and welcome to today's lecture on particle accelerator, specifically the cyclotron. Now, I know that sounds like a heavy topic, but I promise I'll be break it down and make it as clear and approachable as possible. Whether you have a background in physics or you are just curious about how some of the world's most important machines work, this is for you. So today I'm discuss about a cyclotron. So in the very first, what is cyclotron? Let's start with the basic. What exactly a cyclotron is? So, you know that a cyclotron is a type of particle accelerator, a machine that uses electric and magnetic fields to propel charged particles to a very high speed. These particles are typically subatomic, like protons, deuterons, or alpha particles. Once they reach the desired speed and energy, they are used in a wide range of applications from physics experiment to cancer treatment. The cyclotron is one of the earliest types of accelerator, and although it was invented nearly a century ago, it laid the groundwork for much larger and more powerful machines that we use today, like the Large Hadron Collider. A little but a very strong history of cyclotron. So, where did the cyclotron come from? The cyclotron was invented in 1930 by Ernest O and M. Stanley Livingston at the University of California, Berkeley. Lawrence was awarded the Nobel Prize in Physics in 1939 for his invention. At that time, physicists are searching for ways to accelerate particles to very high energies. Linear accelerator or linacs existed, but they are very large and expensive. Lawrence had the idea that instead of building a long accelerator, you could make a compact circular one, and that's essentially what a cyclotron is, a circular pod that keeps particles spiraling around a magnetic field while an electric field accelerates them. And yeah, now I want to say about how to it works. Now let's talk about how it works in a simple term. The cyclotron consists of a very few components: a magnetic field, two hollow D-shaped metal chamber, which are called these, a source of charged particle, and high frequency alternating voltage. So here's the step-by-step formulation. First of all, a charged particle like a proton is injected into the center of the cyclotron. A perpendicular magnetic field is applied across the entire apparatus. This magnetic field causes the particle to move in a circular path. At the same time, an alternating electric field is applied between the two Ds. As the particle passes between them, it gets accelerated. Because the particle gains energy, it moves faster, and that means its circular path becomes larger. So the particles spiral outward in a widening circle. Eventually, when the particle reaches the edge of the cyclotron, it's moving at very high speed, and it's then extracted and directed to a target for use. So, in short, magnetic field guide the particle in a circular path, and electric field accelerate it. Hello good people, now I'll discuss about the role of magnetic field. So try to catch the content. Let's dig a little deeper into the physics, starting with the magnetic field. The magnetic field in a cyclotron is static and uniform, and it points perpendicular to the plane in which the particles move. When a charged particle enters a magnetic field, it experiences a force called the Lorentz force. This force causes the particle to follow a curved path. The radius of this path increases as the particle gains energy. So as the speed of the particle increases, the circle gets larger and larger, forming a spiral. Now here's an interesting detail. The frequency at which the particle goes around is actually independent of its speed. At least for non-relativistic speed, This is known as a cyclotron frequency, and it allows the electric field to be synchronized perfectly with the particle's motion. This synchronization is crucial. If the timing is off, the particle won't get accelerated properly. Now I'll discuss about the limitation. Now the cyclotron isn't perfect. One major limitation is relativistic effect. As particles approach the speed of light, their mass effectively increases, and that throws off the synchronization. The cyclotron frequency begins to change, which means the alternating voltage no longer gives the correct boost at the right time. As a result, standard cyclotron can only accelerate particle to a limited energy, typically a few tens of MeV. To overcome this, scientists developed the synchrocyclotron and later synchrotron, more advanced accelerator that adjust for relativistic effect. Now the most fascinating part of cyclotron, the uses of cyclotron actually. Okay, so we know what they are and how they work, but why are cyclotron important? What are they used for? So there are lots of uses of cyclotron, and among them medical application is a most favorite and most important uses of cyclotron. So in the medical sector, one of the most important uses today is in medicine. Cyclotron are used to produce radioisotope, and most importantly short-lived radioisotope for medical imaging and treatment. For example, PET scan use a radioisotope called fluorine F18, which is produced in a cyclotron. Some hospitals even have their own compact cyclotron for these purposes. Cancer treatment, cyclotron can also be used in proton therapy, a form of cancer treatment that uses proton beam to destroy tumors with high precision. Because proton beams can be focused more accurately than X-ray, they cause less damage to surrounding healthy tissue. Scientific research in nuclear physics and material science, cyclotrons are used to study particle interaction, nuclear reaction, and properties of material under high energy bombardment. Industrial use, they are also used for non-destructive testing, checking for material flaws in structure like aircraft component or sterilizing medical equipment. And now the engineering section of cyclotron, design variation. So now talk about different types of cyclotron. The basic design we've discussed is the classical cyclotron, but is technologically has progressed. Engineers and physicists have developed several variations to overcome limitations. Cyclotron, this type modifies the frequency of the accelerating voltage to compensate for relativistic mass increase. It allows particles to be accelerated to high energies. Isochronous cyclotron, in this version, the magnetic field is shaped in such a way that it keeps the particle frequency constant even as energy increases. That means the accelerating voltage can remain at a fixed frequency. Compact cyclotron, these are smaller machines designed for hospital or small labs, primarily for medical isotope production. They are typically less powerful but easier to maintain and operate. Yes, there are lots of advantages and disadvantages of cyclotron. So first I want to talk about the advantages of cyclotron. So this is very compact compared to the linear accelerator like linac, efficient for accelerating particles to moderate energies, ideal for producing medical isotope on site. That is, as the cyclotron produced radioisotope has a very short half-life, so this is important to establish cyclotron on the site. So on-site cyclotron is very important, and less power consumption compared to a more advanced accelerator. And I have no idea about this actually. Now the disadvantages of cyclotron are energy limitation due to relativistic effect, limited to light particles like protons or deuterons, not suitable for very high energy experiment like those conducted at CERN. Fun fact. So here are some quick facts to keep it interesting. The first cyclotron built by Lawrence was only 4 inches wide. How possible it is? Today's medical cyclotron can be installed in hospital and are often used daily. Despite being nearly 100 years old, the cyclotron design is still in use today. Some modern cyclotrons use superconducting magnet to improve performance and reduce size. Future development. Looking to the future, we are likely to see some compact and powerful cyclotron being developed, especially for medical use. There's ongoing resource into using laser driving accelerator and other next generation technologies, but the cyclotron remains reliable and cost effective. There's also growing interest in automated isotope production system where cyclotron are run with minimal human intervention. In fact, AI and robotics are beginning to play a role in managing this complex. So, what's the summary now? So, to summarize what we have covered today, a cyclotron is a type of circular particle accelerator invented in 1930. It uses a static magnetic field and an alternating electric field to accelerate charged particles in a spiral path. Its primary use in medicine, physics, research, and industry. It has limitations, especially due to relativistic effects, but newer designs have addressed some of these issues. Cyclotrons continue to play a crucial role in science and healthcare. So, to bring us to the end of our lecture, hopefully now you have a solid understanding of what a cyclotron is, how it works, and why it's important, whether you are planning to pursue